A small black panel sitting outside a lab in Shenzhen has been quietly doing something that water engineers have chased for decades. It sits under the open sky, roughly the size of a card table, about 3/4 of a square meter. No electricity runs into it, no pump, no boiler, no grid connection of any kind. Just sunlight hitting a dark, spongy material and seawater sitting underneath it. A small fan, powered by a tiny solar panel bolted to the side, pushes the rising steam into a condensation box, and that's the entire machine. Every single day, without fail, that small setup pulls over 20 liters of pure drinking water out of the ocean, enough to meet the daily needs of about 10 people. Tested against World Health Organization standards, the water isn't just drinkable, it's clean. Researchers ran the material through a torture test first. They submerged it in seawater and spun it at 450 revolutions per minute, nonstop, for 30 straight days, trying to tear it apart the way waves and salt would over years of real use. Under a microscope, afterward, they found 0 detached particles. The structure hadn't degraded at all. This isn't a lab curiosity that only works under perfect conditions. Scientists from the Chinese Academy of Sciences and Shenzhen University built an outdoor prototype and ran it continuously for a full year with 0 utility, energy input, and it kept performing the entire time through heat, humidity, and salt spray. They even piped the output into a test field and grew spinach, corn, and Chinese cabbage with it. The crops came up healthy. No fertilizer plant, no purification chemicals, no electricity bill anywhere in the process. The reason this matters goes far beyond one clever material. The United Nations declared, in a report published this January, that the planet has entered what it calls an era of global water bankruptcy. 4 billion people now face severe water scarcity for at least 1 month every year. Nearly 3/4 of the world's population lives in a country classified as water insecure. And the technology humanity has relied on to fix this for the last 50 years, reverse osmosis. Desalination is powerful but brutally energy hungry, which is exactly why it hasn't reached the people who need it most. That's the gap this small black panel is aimed directly at. If you like videos like this, hit the like button. It takes a lot of research to put these together. And subscribe so you don't miss the next one. Here's where this story goes. You'll learn exactly how this material pulls clean water out of the ocean using nothing but sunlight, why that's such a difficult engineering problem that decades of researchers with far bigger budgets couldn't fully crack it, how the economics stack up against the desalination plants already running in Saudi Arabia, Israel, and Australia, who else around the world is racing toward the same off-grid dream, and where the real limits of this technology still are before anyone should call the water crisis solved. Let's start with the crisis itself, an era with no name until this year. For most of modern history, water crisis meant something temporary, a drought that would eventually break, a reservoir that would eventually refill. The UN report published in January, compiled by the United Nations University Institute for Water, Environment, and Health, argued that framing is no longer accurate for huge parts of the planet. It introduced a new term instead, water bankruptcy. Not a temporary shortage, but a permanent deficit, where withdrawal from aquifers, rivers, and glaciers has outpaced nature's ability to refill them for so long that full recovery is no longer realistic. The numbers behind that declaration are stark. More than 70% of the world's major aquifers are in decline. Half of the planet's large lakes have lost water. 3 billion people, along with more than half of global food production, sit in regions where water storage is already unstable or shrinking. The report puts the annual economic damage from groundwater depletion, land degradation, and climate-driven water stress at more than $300 billion a year and rising. More than 170 million hectares of irrigated cropland, an area larger than the entire country of Iran, are already under high or very high water stress. Think about what bankruptcy actually implies here, because the researchers chose that word deliberately instead of something softer like shortage. A shortage is temporary, something you recover from once conditions improve, the way a bank account refills after a lean month. Bankruptcy means the debt has grown so large over so many decades that recovery on any realistic timeline simply isn't on the table anymore. Aquifers that took thousands of years to fill can't be refilled in a human lifetime once. They're drawn down past a certain point. Glaciers that have already melted aren't coming back this century, no matter what policy changes next year, no matter how much money gets thrown at the problem afterward. That's the backdrop this small panel in Shenzhen is being tested against. Desalination has always been the most obvious answer on paper. The ocean holds 97% of all the water on Earth. The problem was never supply. It was always cost, and specifically energy cost. Why turning seawater into drinking water has stayed so expensive? Reverse osmosis, the dominant desalination technology used almost everywhere today by forcing seawater through a microscopic membrane at extremely high pressure, filtering out the salt as water molecules squeeze through. It's effective. Big reverse osmosis plants can now produce water for somewhere between 40 cents and $1.50 per cubic meter in the best cases. But that number depends entirely on cheap, abundant electricity, because seawater reverse osmosis typically needs somewhere between 3 and 6 kilowatt hours of energy for every cubic meter of clean water it produces, even with modern energy recovery systems built in. That's fine if you're the United Arab Emirates or Saudi Arabia, sitting on cheap energy and government subsidies, building record-setting plants like Dubai's Hassyan facility, which delivers water at around 30 cents per cubic meter. It's a very different story if you're a coastal village in a country with an unreliable power grid, no subsidies, and no capital for a plant that can cost hundreds of millions of dollars to build in the first place, plus years of permitting and construction before a single liter comes out the other end. Global desalination capacity has climbed past 97 million cubic meters a day, but the places benefiting the most tend to already be wealthy. The places suffering the most from water bankruptcy, largely across North Africa, Central Asia, and South Asia, tend to be the places least able to afford the electricity bill that reverse osmosis demands, which turns access to clean water into yet another divide between rich regions and poor ones, layered on top of every other inequality those places already face. For decades, scientists tried a different approach: skip electricity entirely and use sunlight to evaporate seawater directly, then collect the condensation as fresh water. It's called solar-driven evaporation, and the physics behind it are simple enough to explain to a child, the same basic idea as a puddle drying up on a hot day, just captured and redirected instead of left to evaporate into open air. The engineering behind making it actually work at useful volumes, day after day, year after year, without falling apart, turned out to be brutally hard. The material that finally cracked it. Older solar evaporation designs ran into two stubborn problems. First, the materials used to absorb sunlight and convert it into heat tended to clump together over time, which killed their efficiency, the same way tangled hair traps far less light than hair that's been carefully combed apart. Second, those same materials degraded under constant sun and saltwater exposure, cracking and breaking down the way plastic left outside for a summer starts to crumble. Put those two failures together, and you get exactly why solar desalination stayed a laboratory footnote for so long. The materials that were cheap enough to consider building at scale simply didn't survive contact with the real ocean for more than a few weeks at a time. The team at the Institute of Process Engineering solved both problems with the same idea. Instead of a flat layer of light-absorbing particles sitting on the surface the way paint sits on a wall, they engineered a three-dimensional structure: hollow nanoparticles linked together by polymer chains into what the researchers call a nanoforest. Picture the difference between a single sheet of solar panel glass and an entire forest canopy. A flat surface can only catch the light that hits it directly, while a forest, with branches and leaves stacked in layers, catches light from every angle and traps it before it can bounce away. The 3D shape does two things at once. It dramatically increases the surface area exposed to sunlight, which is why the finished material achieves a solar absorption rate above 90%, and the interconnected structure holds itself together under stress instead of shedding particles the way flat coatings do, which is exactly what that month-long spin test in seawater was built to prove. The results, published in the journal Advanced Materials in June, showed the prototype evaporating water at roughly 8.5 times the rate of older solar desalination designs. That single number is the whole breakthrough in miniature. Solar desalination has existed as an idea for well over a century, dating back to crude solar stills used by sailors in desert travelers who had nothing but a pane of glass and a shallow pan of seawater. What never existed, until this material, was a version fast enough and durable enough to be worth building at any meaningful scale. What the economics actually look like. Here's the number that's turned heads outside the scientific community entirely. The research team estimates that after roughly 2 years of operation, water produced by this system would cost less than bottled water without a single kilowatt hour of grid electricity ever purchased to run it. That claim deserves a little scrutiny rather than blind acceptance, because it's a projection based on materials cost and expected output, not a retail price from a working commercial product. But even treated cautiously, it points at something reverse osmosis structurally cannot offer: a desalination method whose ongoing operating cost is close to zero because its only energy input is free and it falls from the sky every day, regardless of the electricity market, currency swings, or fuel prices in whatever country it's deployed in. That property matters enormously for exactly the regions the UN's water bankruptcy report flags as most at risk. A reverse osmosis plant is a capital-intensive, centralized piece of infrastructure, hundreds of millions of dollars, months of construction, ongoing electricity contracts, trained technicians on site to keep pumps and membranes running. A solar evaporation panel built from this material is small, modular, and needs nothing but sunlight and seawater to start producing. It's the difference between needing a government-scale infrastructure project and needing a rooftop. One requires a national budget line and years of permitting. The other requires a delivery truck and an afternoon of installation. There's a second, quieter economic advantage buried in that same zero electricity design. It removes the single biggest source of unpredictability in desalination economics. Energy prices swing with oil markets, currency fluctuations, and geopolitics, which is exactly why desalinated water costs can vary so wildly from country to country, even when the underlying technology is identical. A system whose only energy input is sunlight sidesteps that volatility completely. The panel that works in Shenzhen this month will cost roughly the same to run next year, and the year after that, regardless of what happens to global energy markets in between. How it compares to the rest of the world's approach. The Gulf states remain the undisputed leaders in desalination at industrial scale. Saudi Arabia's newest projects produce water for around 50 cents per cubic meter, backed by cheap solar power and heavy state subsidies. Dubai's Hassian plant, once fully online, is expected to hold the record for the world's lowest water tariff at roughly 30 cents per cubic meter, running at a capacity of 545,000 cubic meters a day. Israel gets a majority of its domestic water supply from reverse osmosis today, running some of the most efficient large-scale plants on the planet. A genuine national security achievement for a country that spent much of its history worrying about running out of water entirely. These are real engineering achievements, and none of them are going away because of a new material out of a Chinese lab. If you're a wealthy, energy-rich nation with the capital to build a plant that size, reverse osmosis at that scale still wins on pure output. But all of those systems share the same structural requirement. They need serious, reliable, often subsidized electricity and serious upfront capital to work at all. That's a fine model for a handful of oil-rich states. It's a much harder model to replicate in the exact places the UN identifies as facing the worst water bankruptcy, largely across North and East Africa, Central Asia, and South Asia, where neither the capital nor the cheap electricity tends to be sitting around waiting to be spent on a megaproject. China's own answer to the water crisis has historically looked completely different and enormous in scale. The South to North Water Transfer Project, one of the largest infrastructure programs ever built by any country, physically moves billions of cubic meters of water hundreds of kilometers from the wetter south to the drier north every year, through a network of canals and tunnels that took decades and tens of billions of dollars to construct. It's an engineering marvel, but it's also a reminder of just how expensive and disruptive it can be to solve water scarcity by moving water around, rather than making more of it where it's needed. This new material points toward a third path that neither the Gulf's centralized megas plants nor China's own water transfer canals can offer: cheap, distributed off-grid water production that could theoretically be deployed panel by panel in exactly the coastal, sun-heavy, cash-poor regions where the UN says the crisis is worst. China isn't the only country chasing this off-grid dream, and it's worth being upfront about that too. Researchers at MIT have spent years developing atmospheric water. Harvesters, panels that pull moisture directly out of the air itself rather than out of the ocean, using nothing but sunlight and specialized gels. A California startup called Atoko, founded by chemist Omar Yagi, is now field testing containerized versions of that same idea, aiming for commercial units by the end of this year, with early designs already proven to work in Death Valley, one of the driest places on the planet. These systems solve a different problem than the Shenzhen material does. Atmospheric harvesters work anywhere there's humidity in the air, even far from any coastline, but their daily output per panel tends to be far smaller, often measured in a few hundred milliliters rather than gallons. The Chinese seawater approach trades that flexibility for volume. It needs a coastline nearby, but a single pane EAL can already produce more than 100 times what an early-stage atmospheric harvester manages. Put side by side, these two approaches look less like competitors and more like complementary pieces of the same puzzle. Coastal communities get the seawater version. Inland, arid, humid enough regions get the atmospheric version. Neither one needs a power plant, a subsidy program, or a spot on a national infrastructure budget to start working. And neither one requires the kind of international financing deal that a Gulf-scale reverse osmosis plant typically takes years to assemble before construction even begins. The limits nobody should skip past. None of this means the global water crisis is solved, and it's worth being direct about where the real limits still sit. The prototype that ran for a year produced about 20 liters a day from a panel roughly the size of a card table. Scaling that to meet the needs of an actual city means manufacturing, installing, and maintaining an enormous number of these panels, and nobody has yet demonstrated what that looks like at neighborhood or municipal scale, let alone national scale. Going from one working prototype outside a lab to a factory capable of producing these nanoforest panels by the square kilometer is a completely different kind of challenge than the chemistry itself, and it's one that has quietly killed plenty of promising lab materials before they ever reached a real customer. The cost projection that beats bottled water is exactly that, a projection built on lab-scale material costs that may or may not hold once a factory somewhere tries to mass-produce this structure at industrial volume. There's also a physical ceiling that solar evaporation shares with every other solar technology. It only works when the sun is out, which means storage, cloudy day performance, and seasonal variation all need real answers before anyone relies on this for a water supply that has to work every single day of the year, not just on sunny ones. A village depending entirely on these panels still needs a backup plan for the rainy season. And brine disposal, the leftover concentrated salt that every desalination method has to deal with somehow, isn't something the published research has fully addressed yet at scale either. At a handful of test panels, leftover salt simply isn't a problem. At the scale needed to supply a coastal town, it becomes one quickly. What happens next? If this technology does scale the way its inventors hope, the impact wouldn't be measured in one dramatic headline. It would show up quietly, panel by panel, in exactly the places that have been locked out of desalination for the last 50 years because they couldn't afford the electricity bill. Coastal villages in water-stressed parts of Africa, small island nations with no grid infrastructure to speak of, refugee settlements near coastlines with no reliable power at all, fishing communities that have watched wealthier neighbors down the coast build reverse osmosis plants they could never hope to fund. Places where a $300 million reverse osmosis plant was never going to get built, but a shipping container of solar panels just might. That's also exactly why this story is being watched well beyond China's own borders. The UN's own water conference, set for December in the UAE, is expected to spend real time on exactly this question. Not just how to build bigger desalination plants, but how to get clean water production to people who will never be connected to one, whether that's through China's seawater panels, MIT and Toko's atmospheric harvesters, or whatever comes next from a lab nobody's watching closely yet. A technology that needs nothing but sunlight and seawater to function. Is about as close to an answer to that specific question as anyone has published in years. And the fact that multiple countries are converging on some version of the same idea at the same time independently is usually a sign that an idea's moment has actually arrived rather than a coincidence. The small black panel outside that lab in Shenzhen isn't going to end the global water crisis by itself, and no single invention ever does. But for the first time in a long time, the bottleneck on solving water scarcity for the poorest, sunniest, most water-stressed parts of the world doesn't look like a physics problem anymore. It looks like a manufacturing and deployment problem, and those tend to move a lot faster once someone proves the underlying idea actually works in the real world, outside, in the salt and the heat, for a full year, without ever asking for a single kilowatt of help. If this kept you watching to the end, hit like, subscribe, and turn on notifications so you catch the next one. Here's a question for you. Do you think distributed off-grid technologies like this one will end up doing more for the global water crisis than giant centralized desalination plants? Or will scale always favor the mega projects in the end? Let me know in the comments. The real breakthrough here is a solar-powered photothermal desalination material from the Chinese Academy of Sciences in Shenzhen University, published in Advanced Materials June 2026. It's genuine, verified, and current. I kept your dramatic title framing but grounded the could end the water crisis claim honestly in the body, with a dedicated limits section, rather than overstating it as solved.